In the previous lecture, I discussed the time reversal symmetry and showed that the Dirac equation does obey this symmetry. The symmetry extends to many other interactions as well, and we have only a tiny violation of time reversal symmetry in the weak interactions. This observation in some sense is hard to grasp, because we have a very strong sense of arrow of time, and so there is enough confusion about how there could be a strong asymmetry in our observation as far as time is concerned, while the dynamical equations show only a tiny violation of time reversal. And I would like to clarify a few points regarding that. The first point is that time itself is treated in quantum theory as a parameter, and we often talk about the system evolving from some initial state under the influence of certain Hamiltonian to a final state. And so, time is the descriptor of the change in the state from the initial point to the final point, and that description as a parameter is quite a different language than treating other objects in quantum theory as operators. And in particular, time and space do get mixed because of relativity, but it is very easy to treat the space coordinates as operator, and you can talk about their measurements and their uncertainty and things of that sort, but time is literally not at the same level. We cannot define some operator whose expectation value will give time. It is not really the part of the formalism as we have developed. And this distinction of treating the time as a parameter and not as an operator opens a new direction in which time can be labeled, and that is provided as boundary conditions on time. So, we have so called time asymmetric boundary conditions which enforce the principle of causality. So, a complete solution to the problem requires always two parts. One is a set of dynamical equations. We have differential equations of various types, and then the boundary conditions which will allow you to complete the solutions, and the equations may be time reversal symmetric, but the boundary conditions may not be, and if that is the case, then we do have a sense of time through the boundary conditions, and this appears in quantum field theory under various labels which go under the names of retarded propagators. There is a trick to ensure this thing which goes under the name I epsilon prescription. Many times the expectation values are evaluated as time ordered products, etc. But all these consequences are arising from the particular boundary conditions that we choose, and that boundary conditions is strongly connected with our sense of time and what we understand to be cause and what will be the effect. So, this is one way of bringing in time asymmetry even when the equations of motions are completely time reversal symmetric. But as I said, there is a little bit of violation of time reversal through the weak interaction, and we have to understand how that also contributes to the observed time asymmetry in the universe, and in particular what we need is a particle antiparticle symmetry in the universe which arises from this time reversal violating interactions even in the presence of this asymmetric boundary condition. So, in our universe these boundary conditions is provided by the so called Big Bang at the beginning of time, and how the system will evolve after that particular instance, and to create the observed particle antiparticle asymmetry from an initially symmetric state, we need certain extra conditions and these conditions or properties go under the name of Sakharov, who clearly spelled them out, and we can now understand what these conditions are in a simple enough language. I will just list them one by one. That we want to go from a symmetric state to asymmetric state, and that clearly requires a contribution to an interaction which breaks this particular symmetry. So, this in our universe the particle antiparticle symmetry is defined in terms of baryon number or lepton number of the various states. So, to produce this symmetry we certainly need a interaction which violates baryon and lepton number. This interaction does exist in the structure of weak interactions, but it is a tiny effect. The second thing which is required is that one has to evolve and produce this effect, and that will not happen unless the evolution rule itself is asymmetric. So, we still need on top of that a property which makes the evolution time asymmetric, and that is the condition that the time reversal or equivalently CP symmetry should be violated. Again, this property exists in the weak interactions, but to a tiny extent. So, these two are there, and the third property which is needed is that one will not evolve from a particular state unless there is a driving force, and if you starts in an equilibrium state, one will always remain in equilibrium state. That is the way we define equilibrium. So, the third condition is that the universe must be out of equilibrium, and that out of equilibrium dynamics will produce the driving force to take advantage of this asymmetry, and this out of equilibrium process arises from a different interaction, and that interaction is gravity. And it is simple enough to understand that a gravitational force which is always attractive cannot come to an equilibrium by itself. You need both attractive and repulsive forces to be able to achieve equilibrium, and a purely attractive gravity always leads to a collapse state like a black hole. So, if you start out from an extended object, it certainly is going to collapse due to gravity, and that is a non-perturbative evolution driven from the extended object to a collapsed object monotonically. And given this dynamics, these three Sakharov conditions, one can understand that you can develop a particle antiparticle asymmetry in the universe, even if the original state was symmetric. To understand the actual observed value of this asymmetry is a much difficult task, and even with all these ingredients, it is a problem which has not been fully solved. There are various models which take advantage of these features and then they give certain estimates, but we still have not developed a model which is completely satisfactory. In particular, there are a lot of conjectures that there must be interactions beyond the usual set of 4 that we treat most often in high energy physics. These 4 consist of the strong, electromagnetic, weak and the gravitational interactions. So, I will leave this discussion of time reversal symmetry, how it is broken, how it can lead to particle antiparticle asymmetry at this particular stage, and further details can be obtained only in detailed calculations and extensions of the so called standard model of particle physics. Now, I want to go to a completely different topic which illustrates many features of relativistic quantum mechanics in a context which is very different than the normal subject of high energy physics. The relativistic quantum mechanics which we looked at requires electrons and protons and other particle moving at a speed very close to that of light, and that occurs only at very high energy processes typically encountered in accelerators and collision processes like cosmic rays, but not in our routine life. And so, many of them kind of remain out of reach of most common situations in physics, but it turns out that there is a new system which has been investigated in recent years, where these features appear in condensed matter physics at a energy level which can be encountered in simple tabletop experiments, and that is why it has been useful as a laboratory tool to understand many unusual properties which we have seen in the case of solutions to the Dirac equation. And I would discuss this thing in a little bit detail to illustrate how the unusual features seen in case of this particular system can be associated with predictions coming from the Dirac equation. And this system happens to be a material called graphene. This is a condensed matter system obeying Dirac equation in 2 plus 1 dimensions. Now, in terms of its material content, graphene is a layer, a single layer of carbon atoms arranged as a 2 dimension in space hexagonal lattice. Now, carbon has 4 valence electrons, and in a hexagonal lattice each carbon has 3 neighbors to which it forms bonds. So, out of the 4 valence electrons, 3 of them are occupied inside the bonds, while the fourth one remains free. In the terminology of chemistry, these 3 bonds form so called sp2 hybridization structure and connect to the neighbors. And the fourth one goes into a so called pi orbital, which lies just above and below the layer of carbon atoms, and that fourth electron is responsible for many of the dynamical properties of this graphene. By dynamical properties, I mean those important at low energy like transport or conduction of various types, essentially described by how this fourth electron is going to move around on this sheet of graphene. And we want to study essentially the dynamics of this fourth electron by looking at a simple model. So, the simple model is provided by the so called tight binding approximation. We have the Hamiltonian of the system, which means essentially this fourth electron whatever it does, and it only has kinetic energy, which is described by some hopping parameter labeled here as T connecting neighboring sites, and the creation and annihilation operators described by A dagger and A. So, this particular term means that an electron at site j is taken out from that particular location and deposited at site I, which is a neighbor of that particular site, and this nearest neighbor coupling is essentially all that remains in tight binding approximation. Because of the translation invariance of the system, there is no potential energy appearing at all. This is only the kinetic energy part, and in real life the objects which appear over here, the coefficients T which describes the strength of this hopping is positive, and the operators which appear in this expression are fermionic. So, they have the anti-commutation rule given by A dagger anti-commutator equal to delta I j. So, this is a simple enough model to describe graphene, and we want to see what this produces when explicitly evaluated on this geometry of this hexagonal lattice formed by carbon atoms, and we will see that description produces Dirac equation for electrons with sufficiently low energy. And in this calculation, I have already made certain choice of units, and that will help to keep the algebra simple enough. So, lattice spacing of carbon atom is just chosen to be 1, and when necessary this can be reintroduced back by dimensional counting. So, now let us work out the details of the lattice structure. I will draw the simple minded diagram for a hexagonal lattice. Where this is a hexagon and the pattern repeats. And so on and so forth. It is clear that there are two type of sites, and I will generically label them A and B, where A have bonds pointing in 3 directions separated by 120 degrees, and B has again 3 bonds separated by 120 degrees, but the directions of these bonds between A and B are different. They are related with respect to a rotation by 60 degrees, and this makes these sides A and B inequivalent, and we will explicitly keep track of this side by introducing a new label, which basically specifies whether the site is of type A or B. And so, we will have a new label which can well take 2 values, and those values are A or B, and we will treat it the same way as we treat 2 values of spin. So, this object is commonly referred to as pseudo spin. It has nothing to do with angular momentum. It gives the position label, and one can now see that this hexagonal structure can be described in terms of a unit cell which periodically repeats over the whole space, and this periodically repeating unit cell can be obtained by connecting the centers of the hexagons, and it has a rhombus shape, and this unit cell contains these 2 degrees of freedom A and B. So, this label of a pseudospin now refers to the 2 degrees of freedom inside a unit cell. So, there are 2 degrees of freedom per unit cell, and we will sum over the unit cells using translation symmetry as usual. And one can also observe that one can interchange these 2 labels by rotation of pi along a axis normal to the sheet of graphene. So, this is a important index and we need to know its meaning as well as how it can be manipulated. Given this label, now it is a straightforward algebra to work out the properties of the unit cell, the Fourier transform version which defines the Brillouin zone, and then do the calculation of the Hamiltonian in terms of the vectors describing the unit cell as well as those corresponding to the Brillouin zone. For that, now we need the various vectors connecting one side to its neighbors, because the Hamiltonian has this nearest neighbor interactions. So, the neighbors of sites A, they are given by 3 unit vectors, and we can easily see their components as B1, B2 and B3 in terms of 3 unit vectors rotated by 120 degrees, and neighbors of B are just given by the vectors directed in the opposite sense. So, for example, on this diagram, this label B1 is here, B2 is here and B3 is here. Now, the periodicity vectors of the unit cells are given by the translation vectors connecting an identical set of sites, for example, A to A or equivalently B to B, and those can be again defined on the same diagram by this so called primitive translation vectors, and they in the convention which I will use are T1, T2, T3 as shown here. They connect site A to another site of type A. So, why these are all B, and we can easily work out what this expressions for this primitive translation vectors are. It is just a combination of 2 nearest neighbor unit vectors added with a appropriate vectorial rule. So, this primitive translation vectors for the unit cell are T1 is equal to B1 minus B3, T2 is equal to B 2 minus B 1 and T 3 is equal to B 3 minus B 2. We are working in a two dimensional space. So, only two of the three vectors are linearly independent, and we can take any two of these three to form that particular basis, and I will work essentially with T 1 and T 2. The third one is just a combination of two, or rather you can easily see that T 1 plus T 2 plus T 3 equal to 0, but somehow it is convenient to use all the three in simplifying the algebra. Okay. So, use T 1 and T 2 as the basis vectors. So, given these primitive vectors, the Brillouin zone is now specified by the so called reciprocal lattice vectors. And that relation is just a orthogonality relation between this reciprocal lattice vectors k and this primitive vector t producing 2 pi times a Kronecker delta. And given these values of unit vectors t, we can easily solve what this k would be, and the solutions are k 1 is proportional to B 3, while k 2 is proportional to B 2, and we can just by analogy extend these two basis vectors to a third one, and I will call it k 3, which will be proportional to B 1. So, now these vectors k 1, k 2 and k 3 form a Brillouin zone, and that Brillouin zone is also a hexagon, but it is rotated by an angle of pi by 6 from the original lattice. So, we can draw it in the same kind of structure which I drew on the previous page as a hexagon oriented as shown, and vectors which we will again connect the centers of these hexagons. So, K 1 points along the direction shown, K 2 has another direction rotated by 60 degrees, and K 3 as I have defined points along a third direction, again rotated by 60 degrees. So, now we have to work out the geometry of this Brillouin zone, and in particular the band structure of the electrons describing low energy excitations is given by the Fermi levels embedded inside this Brillouin zone. The Brillouin zone is again a periodic structure. It has the opposite side identified with each other, and because of that periodicity, out of the 6 corners, only 2 are inequivalent, and we will choose them as the points marked on the diagram. One of them will call K plus, and the diametrically opposite one we will call K minus. In terms of the reciprocal lattice vector, K plus is 1/3 of K 1 plus K 2, and by doing the algebra it is easily seen that this is proportional to the translation vector T 3, and we will define the K minus to be just the opposite of K plus. So, this is essentially all the lattice algebra required now to re-express the Hamiltonian in a form where one can see the excitation spectrum, in particular transforming from the position space to the momentum space through a Fourier transform will allow us to construct the Hamiltonians in terms of the momentum vectors and immediately giving the energy momentum dispersion relation. So, now what we have is a simple structure. Since the Hamiltonian has only terms connecting A sites with B sites and it is Hermitian. So, in the A B basis, the H is off diagonal, and its Hermitian character makes it a linear combination of the two Pauli matrices sigma 1 and sigma 2, we only have a two dimensional situation and only two sigma matrices appear in the Hamiltonian which I started with. But it is possible to get a third term in the Hamiltonian which corresponds to the third Pauli matrix sigma 3, and in this A and B basis it would correspond to situation where the energy at site A is somehow different than energy at site B. It is the diagonal term in the Hamiltonian, and then the atom sitting at A and B cannot be exactly the same, but we can have a same hexagonal structure based on not just a single type of atom, but one type of atom at site A and another type of atom at site B, then their energies will be different and a Hamiltonian will have a third term. So, sigma 3 term can be added when energies of A and B sites are not equal, and a simple example of such a situation is the chemical compound boron nitride. Both boron and nitrogen are neighbors of carbon in the periodic table. Boron has one less electron, nitrogen has one more, and they can form the same kind of bonds as carbon forms with its 3 sp2 hybridized electrons, but the pi electron structure is different for boron and nitrogen, and that makes the energy at site A and B slightly unequal, and that difference produces a sigma 3 term in the Hamiltonian. We can now easily write down the Hamiltonian in terms of a 2 by 2 matrix structure, and that is now so summed over unit cells. We separate out the A and B terms. The sum over the neighbors produce this factors e raised to I k dot b I corresponding to the Fourier transform of that unit vector pointed along that direction b I, and the term on the other side of the diagonal is complex conjugate corresponding to the unit vectors pointed in the opposite directions. Neighbors of A are given by b I and neighbors of B are given by minus b I. And so, we have this Hamiltonian now written in the 2 by 2 matrix form, or equivalently written in the pseudo spin basis. It is Hermitian, and I have written only the examples in case of graphene. If we are looking at boron nitride, then the two zeros and the diagonal can be replaced by two different constants, or if you subtract out a common energy, it can be converted into plus some constant and minus some constant on the diagonal, giving a matrix sigma 3, but I will not discuss this sigma 3 contribution any further and only deal with graphene given by this particular Hamiltonian. Now, we have done the Fourier transform, the operators have been simplified and we can easily extract the energy in terms of the momentum k, and that is very easy to see. The Hamiltonian is traceless, which means there will be pairing of the eigenvalues with every plus e, there will always be a minus e, the sum of the two has to be 0, and the product of these two eigenvalues will be given by the determinant, which can also be easily worked out. Sorry, I made a mistake here in the notation, let me correct it. Okay, it is a summation over I, but the minus I is in the exponent. The determinant is very easily given by the eigenvalue. So, we have the relation that product of plus E and minus E, which is the determinant, or E square is equivalently the negative of the determinant, can be written easily as P square, and these two factors are complex conjugate of each other. So, we have E square is equal to T square times this whole summation modulus square, and that can be explicitly evaluated as three plus 4 times cos 3 k x by 2 times cos root 3 k y by 2 and plus 2 times cos of root 3 k y. So, that is essentially the structure which we are interested in. It gives for a particular point in the Brillouin zone specified by this momentum vectors k x k y, what is the corresponding energy, and that is a description of the band of graphene. Now, to calculate it, one can easily take these functions and plot them as a function of k x y, and it produces a certain surface, and a graphics program can easily show that I am only interested in particular extreme situations, in particular small energy excitations, and those correspond to not the full length or the width of the band, but rather it can be specified by giving the extreme values the energy can take, or rather just the top of the band and the bottom of the band, and everything in between is allowed. So, it can be worked out rather easily from this situation. So, any k y, we have to find out E square is extremized at cos 3 x k by 2 is equal to plus or minus 1, and that implies k x is equal to 2 pi by 3 times some integer, and the extremal values are given by this particular value of k x plugged in, and one can see that there is a particular choice the extreme value turns out to be 0 at cos root 3 k y by 2 equal to half in magnitude, and that means that when one plugs in both this k x and k y, there will be certain points where there are 0 energy excitation available, and these points are given by k y is equal to plus or minus 2 pi 3 root 3 for k x equal to plus or minus 2 pi by 3, and k y is equal to plus or minus 4 pi by 3 root 3 for k x equal to 0, and these are 6 points, 2 here and 4 here, and this point, now one can go back and look at the geometry, are the 6 corners of the Brillouin zone. So, at the corners we have 0 energy excitations, and we will study now the properties of excitations in the neighborhood of these corners in the next lecture.